when we actually solved systems of linear equations using row operations, there were three operations that we ended up using. So we changed the order of the equations. We just interchanged rows. Remember, our notation for that was something like this. Row 1 switches with row 2. We allowed ourselves to multiply an equation by a constant. And our notation for that was whatever the constant was, we wrote the constant times whatever the row was. And then we allowed ourselves to add a multiple of an equation to another equation. And that looked like, say, row 2 plus 3 times row 1, this sort of thing. But for all of this, we were working under the idea that these operations don't change the solutions of the system. And, that seems sort of plausible, but plausibility isn't really enough, right? We have to know for sure that these operations don't change the solution of the system. In other words, we have to prove that these row operations don't change the solution of a system of equations. So let's do that. For one of these, it is obvious that it doesn't change the solutions, and that's interchanging the order of the equations. It's obvious that changing the order of the equations can't change the collection of solutions because the collection of solutions doesn't depend on the order of the equations. It only depends on what the equations are. So changing the order of the equations can't change the collection of solutions. So changing the order of equations is definitely okay. We need to check the others. So how about multiplying equations by a constant? So let's suppose that we have a system of equations. So here's how I will write our general system of equations. So I'll write equation 1, the left-hand side, equals B1. So B1 is the right-hand side of our equation, and E1 is really A11 x1 plus A12 x2 plus, and so on, down to A1n xn. Right? I'm going to be writing these sorts of schematic equations a lot, and so I don't want to have to write this stuff out every time. So, all right, but just remember, wherever you see an E1, it's really an abbreviation for a whole left-hand side of an equation like this. So here's one equation, and then the rest of the equations are all E sub something, all the way down to E sub m equals B sub m. All right, so let's suppose, and what we're going to do is imagine or compare the solutions of this equation to the solutions of, so we need to take some row and just, in general, we can imagine that it's the first row, multiply the first row by a constant. So C times E sub 1 equals, if we multiply this equation by a constant, by the constant C, we have to also multiply the right-hand side by that constant. So C times B1. And the rest of the equations stay the same. Okay, so what we need to do is we need to say we need to suppose that we have a solution. So I guess let me say suppose instead of if. So let's suppose that x1 through xn is a solution to this system. We need to know, is it a solution to this system? So if we plug all of these x's into these equations, it makes them true, right? So if we take E sub 1 and we plug in all of our x's, so this will be my notation for plugging in all of the x's. You have probably used this type of vertical bar notation in some sort of calculus situation. It just means evaluate using these values. And I'm writing an x with no subscript. I guess I should write an x prime with no subscript. I'm writing an x prime with no subscript just to indicate all of the x's with all of the subscripts. So this is just saying take the expression e sub 1, which remember is this whole mess, and plug in the values for all of the x's. That's all this notation means. Well, if this is a solution, right, if the x's form a solution to this system, then that means that when you plug in all of the x prime values, you really do get b sub 1. So this is a true statement. And right, when you plug all of the x prime values into b sub 2, that also is a true statement. And all the way down to e sub m, evaluate that at x, all the x's. And that is equal to b sub m. Well, if we take this expression here, now remember, this expression doesn't, or this equation doesn't have any variables anymore because we plugged in all of the x values that we have. So this is just a true equation, right? There's some numbers on the left and some arithmetic on the left and a number on the right. And when you do the arithmetic, you do get the number on the right. So if we multiply both sides of this by c, what we get is this, right? The constant times all of the arithmetic that we did. But we can distribute this constant into this expression. So that would be c, the constant, times the expression, evaluated at these x values. Okay. So what we've really done is replaced this with that. Okay. And none of these other ones change, so these are all the same. So all the way down to e sub m evaluated at x prime equals b sub m. Okay. But notice that this collection of expressions, so this is just a collection of true arithmetic expressions. This is exactly what you get by taking all the x prime values and plugging them into this system of equations. So what we've proved here is that all of our x prime values from x1 up to xn prime is a solution to the system of equations that you get by multiplying the first one by c, which is this big mess. Okay. So if we have a solution to the, if we have a solution to the original system, then it is also a solution to the modified system after multiplying by a constant. This actually proves it the other way as well. If we have a solution to the modified system, it had to have come from a solution to the original system because we can multiply the first equation by 1 over c, and that means any solution on the right has to be a solution on the left. So all of this says that multiplying an equation by a constant really does work. Okay, when I say it really does work, what I mean is multiplying an equation by a constant doesn't change the collection of solutions to the system of equations. All right. So now we need to check on adding a multiple of an equation to another equation. And this is really the tricky one. So let's go back to our original system of equations. So this was e1 equals b1 all the way down to em equals b sub m. And let's imagine that we've taken some row. In general, it might as well be the second row and add some constant times the first row. Okay. So this would give us the system e1 equals b1. And then for the second equation, we're going to get e2, because that's what we start with in the second equation, right? The second equation is e2 equals b2. So e2 plus c times the first row, so c times e1 equals, so on the second equation we started with b2, but then we have to add c times the first equation, which is b1. And then the rest of the equations don't change, all the way down to e sub m times b sub m. Okay, and now we're going to again suppose that we have a solution, x1 up through xn prime. So what we have to do is check, is this a solution to our modified system of equations? So, well, let's just plug it in and check. So e sub 1, we are plugging in all of our x values, and we want to know, is that really equal to b sub 1? But when you plug all the x values into e sub 1, you have to get b sub 1 because this equation shows up in our original system, and we assumed that we had a solution to this system. So, right, these x values being a solution to the system means that when you plug the x values into this equation, you get a true equation. But that means that exactly that e sub 1 evaluated at all of these x values has to be b sub 1. So this is just because all of our x values are a solution to the original system. Okay, you can see that this same argument is going to show that for all of the equations from 3 down to m, when you evaluate them at our x values, you get the b value on the right that you're supposed to get. Right? So if we started with a solution to these equations and then we didn't change any of these equations, we still have a solution to these equations. So, right, these are all the same. So really, it's only a question of the second equation, which is the one that we modified. Is our old solution still a solution to the second equation? Well, our second equation was, remember, it was e sub 2 plus a constant times e sub 1. And we want to know, is this equal to b sub 2 plus a constant times b sub 1 when we plug in our x values? Well, let's just check. When plugging in some x values into this big mess, it's just the same as taking our e sub 2 and plugging in our x values, and then adding c times e sub 1 and plugging in our x values. Right. But what happens when we do that? Let's look at this piece. What is e sub 2 when you plug in all the x values? Well, if you look at our original system of equations, if you take e sub 2 and plug in your x values, you get b sub 2, because the x values are a solution to this equation. So this first bit is actually just b sub 2. Okay, plus c times, and now what about this second part here? Well, we already said that if you take e sub 1 and plug in all of your x values, what you get is b sub 1. So this part is b sub 1. So on the left-hand side, when we plug in our x values, we get b sub 2 plus c times b sub 1. Is that equal to b sub 2 plus c times b sub 1? Yes, those are exactly the same thing. So every solution to our original system of equations gives us a solution to our new system of equations. And in fact, this whole argument works exactly in reverse, so that any solution to our new system of equations had to have come from a solution to our old system of equations. And that means that replacing this second equation with our modified second equation doesn't change the collection of solutions. All right, so finally we know that this third row operation, adding a multiple of an equation to another equation, does not change the collection of solutions. So all three of these operations are safe operations to use to solve a system of linear equations. The nice thing is, now that we know that these three operations are safe, we can use them freely and not have to worry about this big complicated argument that went into proving that they're safe. now that we know that they're safe, we can just trust that they're safe and not reprove it every time.